Have you ever wondered how Uber Eats actually select drivers for delivery? And it is not as simple as you think. Most people assume that Uber Eats uses the same matching algorithm as Uber Rides. But in ride sharing, it is two-way match. A driver and a rider. That's it. But in food delivery, it is completely different engineering beast because it's a three-way matching problem. The customer who wants the hot food, the restaurant who's cooking the meal, and the courier who's transporting the order. So if you were to write here right now, ask a very naive developer who hasn't worked on any scalable application or haven't seen any scaled application or something like that, then they'd probably say that if I were to build this, then when the order comes in, find the closest courier to the restaurant and dispatch them immediately. But that's a really naive approach, and that would completely fail in production. And to understand, let's imagine you have a pizza bakery and the pizza takes 20 minutes to bake. So if you were to dispatch the closest courier driver instantly, they arrive at the pizzeria in, let's say, 2 minutes. What happens? The courier stands in the restaurant for 18 minutes doing nothing, and they are not getting paid for waiting. They get frustrated and the system capacity drops. Conversely, if you dispatch the courier too late, then the pizza sits on the counter under the heat lamp for 15 minutes. The crust gets soggy, the cheese gets cold, and the customer then demands a refund. So the core problem with Uber Eats is it is not trying to find the closest courier to the restaurant, it is trying to time the courier. So ETA courier matches the prep time of the restaurant with near zero ideal time for both food and the courier. And to solve this, Uber Eats uses something which is called as batched multi-parity matching. So let's go a little bit deeper into it. So the first component of this is the batching window. So instead of matching an order to the exact second you press place order, Uber Eats places your order into a dynamic time bucket, typically 5 to 10 seconds. And during this particular window of 5 to 10 seconds, the system collects all the incoming food orders, active restaurant kitchen status updates, and available couriers within a local area. And every 5 to 10 seconds, the engine builds a graph. Let's say, for example, node A is the available couriers on bike, on scooter, on car, on cycles, all of them. Then there is node B, which is active orders at the restaurant with estimated kitchen completion times. Then there is node C, which is delivery destination, the customer. The second component is the Uber Eats cost function. The algorithm calculates the cost weight for every possible combination of courier, restaurant, and customer with multiple variable questions. Notice the first term, ETA courier minus prep time. The goal is to minimize the absolute difference between when the courier walks through the restaurant door and when the kitchen boxes up the food. So basically, you walk in, you get the food, you go out to deliver. That's it. There should be as little waste of time as possible. So the cost function also considers order stacking, which is called as batching. So can a courier A pick up two orders for the same restaurant or two adjacent restaurants going in the same direction? That is also being checked by the Uber Eats cost function, which is called as order stacking. That's why if you have ever worked in Uber or if you have a friend who's working in Uber, then they might have these kind of experience. You pick the order from one place and then you go on to other place, you pick that order too, and then you go on to deliver that into multiple locations. That's how it works. So once all edges of the cost are calculated, the Uber runs an optimization solver like a Hungarian algorithm or a linear problem programming network to find the global minimum cost across entire city patch. And to run this algorithm, every few seconds, Uber relies on 4 core microservices components. The first component is ML kitchen prep time estimators. So let's say a restaurant tablet says ready in 15 minutes. That is rarely accurate. We all know that if a restaurant says it is 15 minutes, it's probably 30, 45 minutes, something like that. Never less than that. So Uber built a dedicated machine learning model that predicts meal prep time based on number of items, complexity, and current order. For example, salad or a well-done steak. So if it is a salad, it will be probably ready much more quicker. If it is a well-done steak or a burger or something like very complicated or something, then Uber just knows that it is going to take a little bit of time. So also it considers the historical kitchen speed for specific day and time, then live restaurant load, how many other orders are in the kitchen which are currently processing. Then the component number 2 is spatial index, Uber's H3 hexagon. So to prevent searching through millions of couriers across an entire country, Uber uses H3. It's open source spatial index that divides the entire map into hexagonal cells. You can log in right now onto Uber Eats basically, and you can see the entire map is divided into hexagon cells. It is not like square thing or circle or something. It is hexagons. So each hexagon is like divided. So the dispatch engine only compares the restaurant, couriers, and customers within the same neighboring H3, which are basically an hex grid cell, which drastically cuts down the graph size and basically make it very limited. So if you have this H3X and hexagon box, then if you're here, you'll get probably a delivery from here itself, not up here. Simple as that. And the component number 3 is route and travel time engine. So in Uber Eats, the travel time heavily depends upon the transport mode. A bike courier is in downtown Manhattan, travels faster through heavier traffic than a car, but slower in open roads. So the ETA engine also uses custom graph routing algorithm, like a search with contraction hierarchies, tuned specifically for cars, bicycles, scooters, and even walking couriers. I don't know if walking couriers are really a thing or something like that, but maybe there is. Then the fourth and last component is the dispatch engine and stacking control. So once the optimal matches are computed, the dispatch engine locks the state and sends the offer to the courier phone. So if the courier rejects the offer or the kitchen hits a sudden delay, the stacking control dynamically re-evaluates the batch, reassign the order to a better positioning courier or a similar positioning courier without disruptions or the rest of the queue. Simple as that. So by shifting from single proximity matching to ML driven three-way batching system, Uber Eats basically achieve dynamic operational results. So 3 things we get out of this: minimal courier waiting time, courier spends significantly less time unproductively waiting inside of the kitchen, maximizing their hourly earning. The second thing is higher food quality and hotter deliveries. So food spend less time cooling off under heat lamps and leading to lower refund rates and higher customer satisfaction rate. And the third most important one is increased unit economics by stacking. Intelligent multi-order batching allows a single courier to fill multiple orders per hour effectively, reducing delivery cost and also helps them maximize their earning. So the next time when you order, maybe let's say for example your dinner or your lunch, and you see a courier pull up to a restaurant right as your food is bagged, you know it wasn't luck. It was a machine learning model, a geospatial index grid, and multiple variables optimizing the algorithm working all together in real time. So if you enjoyed the system design deep dive, hit the like button, subscribe the channel if you want to know continuously more and more things like this, and if you like this breakdown of me, and leave a comment below telling which algorithm you want me to break down so I can do that next week. Yeah, so see you in the next one.